Okay, I want to take a look at the derivatives of some advanced functions, specifically inverse trig, log, and exponential functions. So let's begin with inverse sine x, which you remember the graph is a reflection of cross y equals x of a basic sine graph that's been restricted to make it one-to-one. Alright, so we got a picture here of the inverse sine graph, and what we're looking for is, as always, a formula that finds the slope of the tangent line at a given point. Remembering now that this is measured is the ratio, and the angle is being measured this way. So we could do this a couple of ways. I'm going to write this as x equals sine y, because these two statements are equivalent, and then I'm going to do the derivative implicitly, which would be 1. Derivative of sine would be cos, and if I isolate dy dx, I get the derivative of sine x, derivative of y, to be 1 over cos, which I could say is secant y. Okay. Now I could leave the formula the way it is, but I'm going to take it one step further because it'd be nice to get a derivative in terms of x instead of keeping it in terms of y. I have my y here. I can bring it down and put it in that spot. So that would be the secant of inverse sine. And now I'm going to simplify this expression, which we've had some practice doing in the past. This represents an angle. Okay, so let's just take this angle piece off to the side, and let's write that as sine theta equals x, because we're more familiar with that format. And let's draw this. Now x is the ratio, which can be positive or negative. If it's positive, the angle is in quadrant 1. X is greater than 0. Can't go above 1 because the sine ratio can't go above 1. It could also be a negative ratio, in which case we are in quadrant 4, because the restriction for sine is between negative pi over 2 and pi over 2. Remember, that's the agreed on restriction we have for the sine graph right here, okay, in order to make it one-to-one. I'm going to take my sine ratio, which is x, or x over 1, and relate that to the y distance over the radius up in here. So the radius would be 1. The y distance is x, and I can calculate that piece right there via Pythagoras. Over where my ratio is negative in quadrant 4, again the ratio is 1. This distance is x, but it's negative because of where we are, and then Pythagoras again. So in both of these situations, these two Pythagoras calculations are going to be the same. The square root of 1 minus x squared, which would make secant, what we're looking for, secant, the radius over the x distance, which would be 1 over the square root of 1 minus x squared. And that is the derivative of inverse sine. Derivative of inverse sine of x is 1 over the square root of 1 minus x squared. And of course we could extend that by the chain rule. If u was a function of x, that would be 1 over the square root of 1 minus u squared times du dx. Alright, now you'll be happy to know that the derivative of inverse cosine is almost the same. It's negative 1 over root 1 minus u squared du dx. And so you need to know both of these formulas. Alright, the next inverse trig function derivative we're going to work on is inverse tan, which, here's the basic tan. So if you reflect the restricted one-to-one function over y equals x, you're going to get this function, and so we want the slope of the tangent line at any given point. And so we can follow a similar procedure. I could set this up as x equals tan y and differentiate implicitly as I did in the last example. I could also just use my formula for the derivative of an inverse, which we know is 1 over the derivative of the original function, which would be tan x, replacing x with y. So that would be 1 over secant squared y, which is cosine squared y. And again, we want to replace the y with a function involving x. Okay, so the y is the inverse tan. Okay, let's just put this all together in one line so we can see it all. We're saying that the derivative of inverse tan at the moment is the cosine squared of an angle which is inverse tan x. Alright? So this is my angle. Let's take my angle off on the side here and draw out what's happening. Tangent theta is x over 1. And x can be positive or negative ratios. And the restricted domain for tangent is negative pi over 2 to pi over 2, non-inclusive. So let's draw those out. We could have the angle in quadrant 1 or in quadrant 4 again. Theta, theta. X over 1 relates to the y over x coordinates on the unit circle, and so we would have the y, which is little x, over 1 here, making this Pythagoras calculation the square root of x squared plus 1. If we were in quadrant 4, this vertical distance is represented by x, which is a negative number here. This is 1, and so by Pythagoras, again, we get the square root of x squared plus 1. Alright, so putting this all together, we're going to get, or we're going to look for, the cosine of the angle. So in both cases, the cosine would be 1 over this square root squared, which makes the derivative of inverse tan 1 over 1 plus x squared. Or by the chain rule, if u is a function of x, it's 1 over 1 plus u squared times the derivative of u. And again, I'm happy to report that the derivative of inverse cotangent is the exact same thing except negative. So that makes that one easier to know. Okay. Alright, the derivative for inverse secant would go similarly. It's a little bit more complicated, and because this doesn't come up a lot, I'm just going to tell you what the formula is, and you need to know it. It's 1 over absolute value x times the square root of x squared minus 1. Okay? And the derivative of inverse cosecant is, you can probably guess, it's the negative of the one above.